Welcome to this video on inequality constrained optimization. Inequality constrained optimization takes the form of this, where you have an objective function f that you're trying to maximize, and some constraint where you have a constrained function g or h, we usually call it, that is less than or equal to a constant. And the idea is that you can maneuver around in your constraint set anywhere up into the point b, and it could be this function exactly equal to b, in which case this is binding, or it could be strictly less than b. And the fact that it could be either complicates the optimization process, which is what we'll be looking at in this video, how to deal with it. In the real world, often our constraints make more sense to be an inequality constraint. For example, if it's the night before an exam, it's 8 p.m. and the exam's at 8 a.m., you're trying to usually at this point in time maximize your grade. And you can choose how long you spend studying for that exam, which is up until 12 hours if you just pull an all-nighter and you keep studying right until the moment you walk in. On the flip side, maybe you want to back off and spend some time resting, and that might have a better effect on your performance for that exam. And in this case, your constraint is you have up to 12 hours to spend studying. You don't have to spend all 12 of them. You can spend up to 12. And this would be a quick example of an inequality constraint optimization problem. Now, sometimes we have problems given to us that are in a form that is a little bit different to this case here with max and then less than or equal to b. And our general form that we use the theorem to solve looks like this: max and then something less than or equal to b. But sometimes just the problem you're actually dealing with and you're looking at is not in this form. And if that's the case, the first step with dealing with these problems is actually converting the problem into this form. So for example, if you were given a minimization problem, instead of minimizing f of x, instead you would want to maximize the negative f of x. And this would be a way to find the same solution in terms of x, achieved in a different way representing the problem. Likewise, if your constraint looked like this, g of x is greater or equal to b, then that is logically equivalent to minus g of x is less than or equal to minus b. And the reason why these semantics matter is that the solution approach that we'll be using will require us to have already converted the problem into the form of max something with a constrained function less than or equal to a constant. And there's a quick example of that. Okay, so new conditions for a local maximum. And I want to look at the intuition first as to where this new condition in our first order condition comes from. If we have our max problem here and our constrained function is less than or equal to b, at the end of the day, there's going to be two options. Either the constraint function is exactly equal to b, or the constraint function is strictly less than b. And if it's equal to b, it's the same process that we're used to where you're solving and looking for tendency condition. But if it's strictly less than b, actually it's another process that we're used to, which is normal optimization, unconstrained optimization, where you're looking for turning points. And in this case, the turning point is inside of this region of less than b. Now, the thing that's complicated is we don't know which one it is. Okay, so two cases. Case one, equal to b. That means that the critical point is on the boundary. The constraint is called binding, i.e. this is exactly equal to b. Grad f is equal to lambda grad g. So the constraint function gradient vector is parallel to the objective function gradient vector. And lambda star is greater than 0. We know that because the economic interpretation of the Lagrange multiplier lambda is related to the rate of change of the objective function evaluated at the optimal solution if you change your constraint constant by 1 unit. So if this is positive, that means that you will increase your objective function if the value here increases, and that is representative of being on that boundary when you're maximizing. Where you'd like to go further, you would benefit, i.e. from this positive lambda, by going further, but you can't. Okay, and on the other hand, the other option, the case, is that g of xy is strictly less than b, In this case, the critical point is an interior point of the constraint set. It's a local max of f of xy generally. The grad vector of f is equal to 0, and the lambda is equal to 0 also. That makes sense because the economic interpretation of lambda is, again, what happens to your optimization solution when you increase your constraint constant. And if you're not being bound at the boundary, if it's not binding, then when you change this, it doesn't do anything. If you are already ignoring the boundary and you relax things further, it doesn't matter. And that's why lambda star is equal to 0. So putting this together, we have our new term that is going to go into our Lagrange function, which is our complementary slackness first order condition, which is lambda multiplied by g of xy minus b is equal to 0. And that comes from this. Either lambda is 0, i.e. this, or your constraint is binding. And the null factor law ensures that one of these two things, at least one of them, is equal to 0. And that is going to be a first order condition that we use in our solution approach. Okay, so hopefully that gives you intuition for this. Now we can more formally look at our Lagrange theorem in this context. So let's go through the details. We've got our objective function f. We have all of our constrained functions g, where our constraint set is of the form g is less than or equal to b. And you can have several of these functions. Suppose x star is in our constraint set and it's a local maximizer of f on C. And suppose the Jacobian of binding constraints is full rank at x star. That's NDCQ, which I'll talk about in a second. Then for our Lagrange function defined by this critical point will satisfy these conditions. That's what the theorem says. So our maximizer x star, so long as the NDCQ is satisfied, will satisfy the critical points listed below. Sorry, will satisfy the first order conditions listed below based off this function. And the idea is that we can therefore look for the solution by solving these and finding candidate solutions to this. Okay, let's break down some of the details more. NDCQ, that's the non-degenerate constraint qualification, and that is talking about the linear independence of the constraints in your problem. And here it's for when they bind. So if your constraint isn't binding, it doesn't matter. You can ignore it in that context. And that means that if you have several constraints, you want to look at the boundary specifically and see along that boundary how many constraints are binding at one time. It might be exactly one, and then gets to a certain point where several constraints are binding at the intersection of those constraint boundaries. And then you need to make sure that that specific point, that those constraints are linearly independent. That's how you check the NDCQ. Okay, and yeah, that's it. So we can now solve these problems by constructing our Lagrange function, which is this, and by solving the first order, solving the first order conditions and then the system of equations that come out of it. Okay, so if we take a look at the three main block of first order conditions, the first one is that Lx1 is equal to 0. So the derivative of the Lagrange function with respect to the input variables is equal to 0. And that will achieve this. And remember, if lambda is 0, that means that our grad f is equal to 0. So that's exactly what we expected. Either the objective function grad vector is parallel or is equal to 0. Okay, these ones here, they will give back your constraint as a first order condition. Notice that it's greater or equal to 0 because in this case, our constraints are inequalities. So that's why we have inequalities here. And then this last one here is the complementary slackness first order condition that we talked about previously, where either your lambda variable is 0 or your L lambda variable is 0. Okay. So I think the best way to move forwards here is to apply this with an example. Okay, the example we'll look at is this one. Minimize 4x squared plus 5y squared minus 6y, subject to the constraint of x plus 2y being greater or equal to 18. Okay, so step one, let's get the format in order. Our Lagrange theorem took the form of solving max problems. So we're solving max problems, and our constraint functions need to be of the form constraint function less than or equal to a constant. In this case, constraint function is not less than or equal to a constant, so we need to work on that. And we have a minimization problem, so we need to work on that as well. So we can transpose this problem where the minimum of this is logically equivalent to the maximum of negative this, and our constraint is logically equivalent to this by taking the negative on both sides. If this number is bigger than this number, then the negative of this number has to be smaller than the negative of that number. Okay, and all up, we get this transpose problem now in the correct form with a maximization optimization command and a inequality with a function less than or equal to a constant. Okay, step 2, check the NDCQ. So because we have one constraint, we can work out the gradient vector of our constrained function. In this case, it's just minus x minus 2y. And that's the constraint function. And then the gradient vector of this is minus 1 minus 2. That's never 0. So as the only constraint grad vector, it's always linearly independent to itself. Therefore, the NDCQ always holds. Easy. Step 3, we construct our Lagrange function. So we have our objective function minus lambda, our constraint. So that's just putting that objective function straight in, and then minus lambda, the constraint. And notice how this gets moved to the left-hand side so that it's 0 on the right there. Okay, next is we need to list our first order conditions. So what's highlighted in orange is new and specific to our inequality constrained setting of Lagrange, but we can look through all of them. First of all, we have the input variables. Sorry. We have the input variables being differentiated and set to 0. And so just following through this with the derivative and setting it to 0 gives us 1 and 2. Next, we differentiate with respect to lambda, and our first order condition is that derivative being greater or equal to 0. That's important. It's not equal to 0 like our previous constrained setting, but it's greater or equal to 0 to respect the fact that we have an inequality constraint. And then 4 is complementary slackness. Either lambda is 0 or the constraint is binding. Those are the two alternatives. And then 5th is not a first order condition as much as it's a requirement for all of the conditions above. It's a 5th condition generally, and that is that lambda is greater or equal to 0. So that makes sense. If lambda was negative, then you would be at the boundary and you would benefit by relaxing your position not in the direction that you can't go in, but just towards the other direction. That's what a negative lambda would suggest. And for that reason, it can't be a max then, which is how we know it must be either 0 or positive. Okay, so now we need to take these conditions and find an x, y, and lambda where all of these conditions hold. And honestly, the approach for doing that is not always linear, but it's a systematic search through the conditions to find information along the way that we can use to work out what's going on. So the first thing that I would consider is like, look, either lambda is 0 or it's positive. That's true from 5. It's either 0 or positive. And the impact of that on 4 is pretty big. If it's positive, if lambda is positive, we know that x plus 2y is equal to 18. So we can work with that as a starting point to say, okay, if it was 0, what would happen? And either we will find a solution or we'll prove that it's not 0, and then we can proceed from there. Okay, so let's go ahead and do that. So either lambda is equal to 0 or it's positive. Let's consider when lambda is 0 and then see what happens. See if I can keep those first order conditions close by. Okay, so if lambda was equal to 0, then equation 1 becomes minus 8x equal to 0. And so clearly x is equal to 0 as well from that. And then for equation 2, y must be equal to 0.6. So if lambda is 0, we know x is 0 and y is 0.6. And that collectively gives us a critical point of this. And we need to check, does this satisfy all of the conditions? Well, 1 is true, that's how we worked out x. 2 is true, that's how we worked out y. What about 3? 0 plus 2y minus 18. No, that's just not true. That's not greater or equal to 0. So that's what is going to be said below. Here, if we look at 3, we do not have this inequality holding. Therefore, we have a contradiction, and therefore we reject this, that lambda is equal to 0. So our conclusion is clearly lambda is not 0. And from knowing lambda is not 0, that's really helpful because we know that lambda must be positive. Okay, so that's our first step in solving this is establishing lambda is not 0 and that lambda therefore is positive. Knowing that, we can move forwards with what's going on. And 1 means that 8x is equal to lambda. And 2 means that 10y minus 10y plus 6 plus 16x, just plugging in 8x equal to lambda, is equal to 0. And altogether that gives us x equal to 10y minus 6 on 16. And because lambda is not 0, 4 implies that x plus 2y minus 18 is equal to 0. So we have a second equation, and we can combine those two together simultaneously to solve for x and y. And that gives us y is equal to 7, and then x is equal to 4. And then using one of the other equations left over, we can work out lambda is 32. Easy. So we can check that all of these equations hold. Minus 8 times 4 is 32, plus 32 is equal to 0. Tick. Minus 10 times 7 is 70, plus 6 is minus 64, plus 2 lambda, so that will give us 0, tick. X plus 2y minus 18 is greater or equal to 0, so 4 plus 14 is 18 minus 18, that's equal to 0, so that is tick. And then 4 plus 14 is 18, yeah, so everything there holds, and then lambda is equal to 0. So just checking off those conditions, we can see that 4, 7, and 32 as our x, y, and lambda satisfy all of them, and therefore is a critical point. Great. So are we finished? No. So we're not finished because this is the difference between necessary and sufficient. We go back to the theorem. If I can extract it correctly. The theorem says that the solution, if the NDCQ holds, will satisfy all of this stuff. And that means that this is necessary for the solution, but it's not sufficient. It's not double arrow where this implies solution. Just solution implies this will happen. And that means that this point could be a solution where the theorem correctly says it will satisfy all those conditions, or this could just be a random point that serendipitously satisfies those conditions. We don't know. And that's why we need to do a second order test to determine that this really is a maxima and hence the solution to our problem. Okay, so to do that, what test makes the most sense? Well, I like to look at the constraint function first of all, and x plus 2y greater or equal to 18 is an unbounded region beyond a line. So we can't use the extreme value theorem because it's not bounded. But it is a very simple constraint function that will have a simple constraint set that is convex. And our function here, x squared plus y squared, as a min, I'm just thinking that that there would be y is equal to x squared, and it will have a minimum. So from an intuitive point of view, x squared plus y squared, this is going to have some sort of minimum, and then minus 6y won't change the narrative. And then when we transpose that into max of this, it's the same thing flipped upside down. It's going to have a maximum. So to me, that says concave programming makes the most sense. And yeah, let's do that. To analyze it in terms of a concave program, we can work out the Hessian matrix, which is taking the derivatives of our objective function here, differentiating them twice in all of the different possibilities and chucking it into the Hessian, which gives us this. And then d1 is minus 8, d2 is 80. That is a negative positive pattern, which is negative definite, which means f is concave. And that makes our life really simple, because now we have a constraint set that is convex, a function that is concave, and according to concave programming together, that means that there must exist a maximizer. And if there exists a maximizer, that maximizer using our other theorem must satisfy these conditions. And the only thing that satisfies these conditions is the point 4732. So that is how we know that it's the solution. And so then we conclude. Therefore, 47 is the global max of f on the constraint set C. And if that's the global max of f on the constraint set C, it's also the solution to the minimization problem of our original pitch of the question. Right, that's the end of our example. And just to finish this video, I want to touch on the Kuhn-Tucker theorem. So we just looked at the inequality constraint first order conditions for our standard Lagrange function, but there's a similar theorem that I just want to touch on as we finish, called the Kuhn-Tucker theorem. And this is almost exactly the same as what we just did, except our constraint setting has these extra conditions where all of the inputs are positive. So x1 is greater or equal to 0, x2 is greater or equal to 0, all the way through to xn being greater or equal to 0. This is another layer of constraints that make our constraint set more restrictive, I guess. And instead of using the previous theorem and just modeling all of those constraints as extra constraint functions, we can use the Kuhn-Tucker theorem to condense it down into just one smaller problem. It's still going to be big, to be honest, but not as big as if we put all of those inputs as their own function. And yeah, the Kuhn-Tucker theorem, what it does is it has the same context as before, but then when you look at your Lagrange function, you can ignore these inputs as constraint g's and instead have a slightly different modification of your first order conditions. So if you skip down here, you construct your Lagrange, your Kuhn-Tucker Lagrange function based off just your g functions that aren't related to the inputs. And then you use these first order conditions, and solving these ones will give you your solution. And the main differences here is that Lx is now less than or equal to 0 as opposed to exactly equal. And then we have these extra ones, which is very similar to complementary slackness. Either x1 is equal to 0 or it's not, and your derivative is going to be equal to 0, which is why it's not. You're either at the boundary, which is in this case x1, or the derivative somewhere else is going to be 0 and it's going to be your optimal solution. And these ones down here are exactly the same. The solution approach for this is very similar to the standard setting, but just a slight modification of these first order conditions to account for the fact that you have those non-negative input restrictions. All right, that's the end of this video. I hope you found it helpful in understanding constrained optimization when your constraints are inequalities. Yeah, thank you for watching.